Okay, welcome everyone to lecture number 9 of the course. So we are in the last third, if you could say that. Okay, so what have we learned so far? Just revising a little bit. So our aim is to learn PDEs, or rather the solution operators of PDEs from data. And to do that, we are going to use operator learning. And we have seen lots and lots of different examples of that now. FNO, convolutional neural operator, vision transformer, scalable operator transformer, and the list goes on. And what we saw in the last lecture is that as long as you are on a Cartesian domain in 2D, so you know squares, then this is fine because we essentially treat it as images and process them accordingly. But there are many caveats, and in the next 4 lectures that I have, what I'm going to do is to focus on those caveats and try to explain how these can be overcome, how these difficulties can be overcome, how these problems can be remedied, right? So what are these caveats? So let's start with the very first one, which is on the next slide, and that is going to be the issue of time-dependent PDEs. So we have already considered time-dependent PDEs, right? It's not like we haven't considered. If you remember, Navier-Stokes is very much a time-dependent PDE. I'm not going to write down the equations, but it's very much a time-dependent PDE. But what we did is that our solution operator, given the initial data U0, what it did is that it mapped it to some solution at a later time, or solution at a final time U of t, right? So you start initially and you try to predict what happens at time t equal to 1 in 1 hour or 1 day or whatever is the time scale that you're considering. And this is exactly sort of the mode in which our models, our AI models, were deployed, right? That we start with some initial conditions and then we say what is the solution at a later time, which is okay because it's exactly the same sort of a throughput as what happens if you take a steady state equation, for instance a Poisson equation, and then the solution operator was simply a mapping from the forcing term to the solution because there is no time now, so it's mapping forcing term to the solution. So we are essentially treating a time dependent PDE, so this is time dependent and this one is time independent in the same manner. We didn't really differentiate between them. Is that clear? So we took some input, which could be a forcing term, which could be a coefficient, which could be an initial condition, and we mapped it to an output, which could also be, which could be the solution for a steady state PDE, or it could be the solution at a later time for a time dependent PDE, and we really didn't distinguish between them. But in practice, there is a difference, right? Because there between the two, we have a distinction. And this distinction is essentially given by the arrow of time. Time is a very special dimension. It's not exactly the same as the spatial dimensions, right? And time-dependent PDEs have their own special properties. So what we are going to concentrate in the beginning of today's lecture is how we can treat time-dependent PDEs, where the mapping might be more complicated than just going from the initial conditions to the final time. Okay? So let's try to focus on that. Everyone understood the objective? It's sort of a very clear objective. What are the differences and how we take into account these differences? Okay, so now let's focus. We have to sort of start with some math. So now time-dependent PDEs have a very abstract, or the most abstract form. We can write them like this. You can think of the Navier-Stokes equation. So the momentum equation would be ut plus u dot grad u plus the gradient of p equals to 0. So this is the Navier-Stokes equation. I'm not writing the continuity equation, it's implicit. Okay, so you have a differential operator L, which is a function of x, a function of u, a function of x, t, function of u, and its derivatives, right? So here, for instance, the first derivatives of the Navier-Stokes, I wrote the Euler equations. The Navier-Stokes equations would have the viscosity, so mu Laplacian of u. So the derivatives, the gradients of u, spatial gradients, not temporal gradients, right? I did not use high order derivatives in time. For instance, in the wave equation, you have 2 derivatives in time, but to me that is not an issue. Can you tell me why? I can take any derivatives in time and I still only need to consider the sort of the first order derivative in time. Can anyone tell me why? So in other words, what is the connection between this equation and the wave equation? Utt minus c squared Laplacian of u equal to 0, right? So here there is a second derivative in time, but I say that all the equations with second, third, fourth derivatives in time, I can subsume them in this form. Is that clear why this can be done? Yeah?
You can create a system.
Yeah, exactly. So what you could do is that you create a system. So this is what you might have learned in ODEs, that all that you might have 10th order derivatives. It rarely happens that we look at 10th order derivatives in time. Usually look at the first derivative, which is usually the velocity of displacement. Second derivative is acceleration. Rarely is a PDE with a third derivative in time. There are some esoteric ones, but they are very, very rare. But what you do is that you just write them out as a system, right? Because I never told you what is the dimension of u. This could be a vector. So this is, so you make the displacement unknown and you make the velocity an unknown, and then you can do that, right? So this is the abstract form that works for almost all time dependent PDEs. There are some exceptions, but this is the abstract form that you'll work with. Now the solution operator in this case is a more tricky thing. It's not just the mapping between the input and the output as you saw here, but it has to take time into consideration, right? That's why I said that time is a special variable. So what it is that I need a function space, right? Because my initial conditions, for instance, live in the function space. I'm saying that my boundary conditions are fixed, just to make our life simple, because it also depends on the boundary conditions and so on. But the initial conditions are in the function space X. So the mapping, you expect that it's not always the case, but you expect that if you start with the function space, you remain in the function space. And this is a simplified situation. It often happens like that. Okay. So what you do is that this is a function of time and of the initial condition. And given the time, given the initial condition, given what is called a lead time, t equal to 1, t equal to 2, t equal to 10, what you want the solution operator to map is to go to the solution at that particular time span. Okay, so this is the solution operator of a time dependent PDE. It depends on time itself and not just on the input, right? So it's a function, it's a time dependent function, or time dependent operator rather. And in particular, as you can imagine, what happens is that there is causality, there is a march in time, right? We can always march in time. You'll see that graphically in the next slide. So what happens is, or maybe I can already sort of show you. So you start with some initial conditions. So you have, let's look at this. So this is time, right? And we start with some initial conditions. This could be something like this. Then you go to a later time. This could be something like this. So this is t equal to 0. This is t equal to 1. Then you march on, t equal to 2. This could be something even flatter. Who knows what happens, right? So this is how the solution, it's like a video, right? The solution keeps on evolving in time. And the point is that to find the solution at t equal to 2, there are different things that you can do. You can, for instance, say that I start with the initial condition, right? So I start with the initial condition and I go all the way to t equal to 2. So in other words, to get u at 2, I can take s, put 2 as my time and start with u at 0. This is one possibility. But on the other hand, we know that this solution operator is what is called a semigroup. So what I can also do is I can go like this. I can start at t equal to 1 and then march 1 in time. So u2 is also given by 1 and u at 1. Right? Agree? So there is this causality. So things are causal in the sense that the past determines the future. Right? So to reach here, I can either you give me the initial conditions and I can march all the way forward, or you just give me the initial conditions or give me the conditions at t equal to 1 and then I march one step forward or one time forward. Okay, so and there are many, infinitely many, or uncountably many combinations that you can think of. Okay, is that clear? So this will play a very vital role in what I'm going to say. So it's important to understand that. So in other words, for any time increment, this is why I said for any time increment, t delta t, you can march forward in time and the operator takes you here. So once you know this operator, you can start initially and you can go to any time, but you can also start at any time and go to any forward time. Okay, so it's always forward causal. Some systems are time reverse, so you can also come back in time, but most systems are not like that. So using the weather today, you can predict the weather tomorrow, but the other way around is difficult because the weather has some non-reversible, irreversible effects. But this is an important distinction, right? So the data for a time dependent problem, just think about weather for instance, the data for a time dependent problem can be when we generate the data either by numerical simulations or by observation, it is a bit more subtle. So we have an initial condition and we want to find the solution at a later time, but to get that solution at a later time we give the entire what is called a trajectory. So you have u of t1, u of t2, all these time bins, or in other words, if you look at my picture here, the data is not just, so when I march forward and I observe a system in time, I don't just observe the solution at a particular instance, but I observe it along the entire trajectory, along in principle all points in time, but in practice of course we cannot store at every single time point, we can only store at a discrete set of potentially heterogeneous unrelated time points, but the data could be, let's march forward t equal to 3, and then now I'm running out of colors, green is not a good color. So let's go to presets and let's use a dark blue. So it could be something very, very pointed, something like this, right? So you have this entire collection of data, and whether you observe or whether you simulate, you are not left with just one data pair, you are left with this entire trajectory. Okay, so this is the entire trajectory which is given here, and you can think of it as solution at t1, solution at t2, solution at final time, and so on. You can also think of it in this time marching manner. So the data for a time dependent problem is in a way richer and in a way has more structure to it than data for a steady state problem. Because in a steady state problem you just give the inputs, boundary conditions, coefficients, and you read off the solution. For a time dependent problem it's more complex. You give the initial condition, boundary condition, coefficients, parameters, and you read out this entire trajectory. Okay, so there is first of all more volume of data, more to deal with, but more to play with, right? So this is an important distinction. So remember that already there is a big distinction between the two in terms of the data acquisition and in terms of the data handling, because there's much more data in a time much more data in a time dependent problem. For instance, I can tell you about the weather data that we have. I don't know if you'll have the time to explain that, but the weather data is very high quality observational data. It's called ERA, reanalysis data. And this is depends on what data set you're looking at, but essentially you can say every hour, okay, of the state of the global weather, or every 6 hours for sure, but every hour from 1970s, let's say, to now. So 50 years of data, but the data is stored at every hourly interval, so 6 hourly intervals. So there are 4 data points a day, 365 days a year. So you can do, it's like 1500 data points or 1500 images or snapshots you could think of, and over 50 years. So it's a lot of data. So that's why, and there are various variables, right? So it's essentially like many petabytes of data. So this is a much more data rich problem. But of course the task itself is harder, because what will be the operator learning task? The operator learning task, as I have written down below, is given my initial conditions, given my boundary conditions, which is of course implicit, I did not write them down for notational brevity. Then you have to generate, just like if you have a PDE solver, a PDE simulator, given the initial conditions and boundary conditions, it can generate the entire trajectory. Okay, it can generate the entire trajectory. You require the same requirement now. So you generate the entire solution trajectory for all times t. Okay, so in principle all times. In practice this will be a discrete set of times. We could interpolate. So in a way there is also continuity in time, right? It's not just, this is why I wrote down, it's continuous in time, not just in space. So remember, one of the points about operator learning was that you just don't look at vectors, discrete versions of functions, but you want to sample the entire function itself in space. For a time dependent problem, you have to sample the entire function not just in space but in time. Okay, both. So you have essentially the entire trajectory of the solution, and this is why the task is harder in some sense, because not only do you have just been given the initial data, boundary conditions, you generate the entire trajectory, the whole video, or right? So is this clear? Are there any questions here? Because the difficulty of the task as well as what we have to deal with is different. So I'm happy to take questions at this juncture. No? Everyone understands? Okay, good. So now this is the structure, this is the system. Let me give you a concrete example so that you understand what's going on graphically. So this is an example. I think one of you answered this question. So we took the wave equation, right? So this is a concrete, well, it's a toy model. We can show you some real models later on, but this is a concrete toy model. So what you have is just imagine that you have under the ground, and you generate explosions, for instance, by detonating, right? This is very common. We have to do that, for instance, to excavate mines, or imagine that these are small earthquakes. So this is how your ground looks like, right? Rock. So this is different layers of rock. So you have different material properties. So this C here is a function of x, and it has a structure. It's a variation in x, space and time, in space, not in time, right? It changes very, very, very slowly in time. Means it changes over millions of years. But if you want to make some explosions under the ground, this is in a time scale of seconds, right? And then you set off, then this is there. So this is a coefficient. This is one of the inputs, C. The other input is the initial condition, U naught, right? So these are the different points at which these waves are generated. And then the system is sent into the wave equation, the evolution of the wave equation, and you make different observations. So delta t is not a small time, it is some non-dimensional time that I have, lead time that I put in. So in the beginning you can see that the waves, initially the waves are spreading, they are starting to interact. At t equal to 2 delta t, these two waves meet, they start to interact. At t equal to 3, the 3 waves meet. At t equal to 4, the 4 waves meet, and so on and so forth. So this is going to be, so your data, so remember that what is our operator learning task? So we are going to do operator learning here. So what is my what is my task? My task is, this is important, given U naught, this is the initial data, and the coefficient C, because the property depends on the coefficient C, learn ST. Okay, let me write it like this, or I didn't write it the right way. So S, this is the solution operator at any given time t, given U naught and C. So this is going to be my task in a way, right? So I have to learn the operator at any time t. And what is the data? Data is you put a probability distribution, mu, making a lot of mistakes in writing things. So now you put it's a probability distribution on, I don't know, U0 x cross C. So these are some function spaces that I have taken into account. Samples. So these are U naught I, the ith sample, Ci, the ith sample, and trajectories, right? So this is U at T1 I, U at T2 I, and so on till U at TKI. So this is going to be my data set, right? So and I is the variable, 1 less than I less than n. And k is the number of points that I can observe per sample. So each of these, so look at the difficulty here, each of these guys is a function, right? It depends on space, it's a function, and the number of times that we can observe depends on the numerical solver that we have, depends on the storage facilities that we have, depends on the observational systems that we have, and the times at which you observe might not be the same, right? They could be very, very different. We do an experiment here, someone does an experiment in Bern, they might, the measurement apparatus could be very, very different. So this is going to be my data. This is in this form, it's in the form of these trajectories, and I have to learn this entire solution operator at any given time. Okay, so is the operator learning task clear? Okay, good. So now how do we solve this, right? So remember, there is a qualitative difference between the time independent case, because in the time independent case you did not have this pesky parameter, which is this causal structure. It's not just some random structure, it's a causal structure, and your data was much more sparse in a way. This is more dense data. Okay, so in principle, and this is an important point that I want to emphasize, sometimes people don't understand this, that this is the operator learning task. This is the only well-posed operator, that given the initial conditions, given the boundary conditions and coefficients, the solution operator of the PDE is well-posed. Often what people do And in the vast majority of cases, what people do is that they say, no, we are not going to do this. Since we have this time information, we say that we have, let's say, 100 time steps, we will generate 50 time steps, and then we'll predict the next 50. Okay? And this is, I would say, even a crime in this sense, because numerical, this is not a well-posed problem. For the weather system, it is okay, perhaps, because you have constant stream of data that is coming in. But for most applications, you will not be given this rich set, that you already have a trajectory, and then you want to predict half the trajectory and you want to predict the other half. This is not a well-posed problem. What is well-posed is from the starting point and with the initial and boundary conditions, if you march on, right? So this is what is well-posed. But many people don't do that. They say, no, let's give half the trajectory and we predict the remaining half. That is not going to be that useful. Huh? So it's sort of an important distinction that needs to be made. Okay, so let me now try to solve how we can address this. There are different ways to address this, understandably, and they're related to what we have done before, because the new variable is, of course, time. We just have to adjust how time is interpreted or how time is used in this context. Yes, ask.
And once I have this operator, is it okay to apply it kind of recursively?
Yes, absolutely. This is what I'll show you. It's completely okay, because this operator is having this semigroup property that given at, as I told you, given at any, so I need not, in principle, once you have this operator, to go up to here. It's enough if I start here, right? Because then I can either go here and then here, or I can directly use t equal to 2 and go, right? So this is completely kosher. There's no issue with that, right? What is not clear is if you just give this operator or give these 3 steps, it's unclear if they correspond to this operator, what is the initial conditions. There is some unclarity, there is lack of specificity. And so it's important to have this setting that I just explained to you. Okay, so this is precisely the point that I'm trying to say. Yeah. So this is, in particular, if you have uniform time points, it need not be uniform, but for notational simplicity, I put uniform time points. What people often do is precisely what you just said, which is autoregressive rollouts. So what is the meaning of that? So you pick a time point. So this could be this delta t. That's why on purpose I had something which is uniform. So you choose a uniform time point. You know that tk is equal to k times delta t, where k is your running index. And then you define your neural operator just to predict the next step. Okay. So given a time step tl, what the neural operator does is that it predicts the next step. So in other words, given the initial conditions, I predict the first step. And then how do I go to the second step? I take the first step and then march again and do the second step. Then given the second step, I march the third step, fourth step, and so on. Right? So this is the idea behind this autoregressive rollouts. You keep on, you train the operator to just predict for the next time step. Okay? This is what a numerical solver often does. In a numerical method, what we do is time marching, even for ODEs, right? You take ODE, you discretize in time. So given initial time, you go to the first time step. Given the first time step, you go to the second time step, third time step, fourth time step, and so on. So this is one way in which, a very common way in which numerical analysis, numerical methods for differential equations work, right? And this is a very, very useful way. So all that you have to do is to learn the next time step and then autoregressively apply the operator. So is this clear what autoregressive rollouts mean? So you train it for the next time step, you have a large data set, right? So, and then what you do is during inference, I want to sit at this, I want you to predict this. So you start with the initial conditions, apply it once, apply it twice, apply it 3 times, 4 times, 5 times, right? And similarly, you keep on doing as you do. So what is the problem? Well, this is not, usually it requires, you can modify it a little bit, but in the simplest setting, it requires uniform spacing, because you have learned, given a certain input and given time t equal to 1 hour, what happens in 1 hour. You haven't learned what happens in 2 hours. For 2 hours, you need to apply the 1 hour operator twice. But what happens at 1.5 hours, right? Then how do you do this? So what you have to do is you apply it from 0 to 1, then you have to go from 1 to 2, and then you interpolate between 1 and 2, right? It's not a continuous evolution, so it requires uniform spacings. And the main issue is that you have error accumulation. What does it mean? And this is well known in numerical methods that when you apply it once, you make a certain error. When you apply it twice, the potential is that the error is additive. You have 2 times the error, 3 times the error, and so on. So this is what could be very, very risky. And also there is no continuity because the evaluation is at discrete time levels. So as I said, to go in between, I have to use interpolation. So it is a little bit like the CNN plus interpolation approach that we did. We predicted a few time steps and then we interpolate. Can be done if you have sufficient density of points, right? But that's not the main issue. The main issue is actually the potential for error accumulation, right? And this uniform spacing, which is okay for weather prediction, because weather prediction people are interested in what happens in 1 hour, in 2 hours, in 3 hours. So weather predictors, AI based weather predictors, emulators, they usually do this kind of autoregressive rollouts. So to predict the weather in a day, what they do is that they predict the weather in 6 hours, then 12 hours, 18 hours a day. So this is a very, very common thing. But in general, in engineering and science, this cannot be done because you need solutions at discrete time points. And this is an issue. But this is very much a viable option. The second viable option, which is what I would say is a better option in some sense, is what is called time conditioning. Because the issue here is that this was just discrete and interpolation, right? This is much more of a continuous time interpolation. I don't know why I said CNO. It must be any NO, right? Because why CNO? This applies to anything, but maybe CNO was an example. Okay, now I understand. So here is CNO is an example. So what do we do in time conditioning? Is that you use the time itself as an input channel. Okay, you use it as an input dimension. If you remember my solution operator, okay, there's so many things I have written. The solution operator has time as an input, right? So just we replicate that and use time as an input also for the machine learning task. Okay, so you want to put time as an input. So what do? You are given the solution at time t, and you are given the time, or what is called the lead time. T bar means no one gives the absolute time. You can also give it, but in practice it makes a lot of sense to give the lead time because you don't know from where you're going to march, right? So given these two, CNO or any other neural operator, CNO is shown here for concreteness. What you do is that you make a prediction, which is S, you learn the solution operator, which given the current state and given lead time predicts the solution at the t plus t bar time, right? So this is really an approximation to the solution operator, not by composition, but directly. So that is the sort of difference from the autoregressive rollouts. But the question is, how do we apply this time, right? The simplest way is just give it in the beginning. Just like we give the initial data or the inputs, just give it in the beginning. In general, that is okay, but after some experiments, people realized, or we in particular realized, that you tend to forget. So just imagine that instead just you give the input plus you give the time, lead time, right? And then what happens is that you have 20 layers here, you have bottlenecks, you have residual connections, you have all kinds of funky things that are happening. And by the time you come to the bottleneck, the effect of time is the embedding of time is somehow gone, and the causality, the sort of temporal behavior can suffer. In general, this is a viable option. Just put it as a lead time. So what people figured out is to use normalizations to put explicitly time after each layer. So this is where, and how do you do it? Remember, in machine learning, you have MLPs, you have convolution or attention, like a sort of an engine, a kernel, and you have normalizations, right? So this is the structure that we have always dealt with, and in the there's no point in putting it in an MLP, there's no point in putting it in attention convolution. These are time independent operations. So where you put it is in the normalizations. So what you do is, remember, this is a layer normalization, for instance, that the input is given, so you take a mean over all the channels, you take the variance, and this is the usual sort of layer normalization that you do, right? Last lecture I explained this in quite some detail, and then in addition to it, you conditionally normalize it with some time in embeddings. Okay, so these are this GN and HN. These are MLPs. So at every layer, you are sort of giving time as an input. You give a time as an input here, time as an input here, time as an input here, here. Everywhere it remembers that, oh, this is the lead time that I'm going to predict on. This is the lead time that I'm going to predict on. In general, you can use MLPs, but linear layers suffice. So you can just use some matrix vector multiplies. That's good enough. And you can use all kinds of normalizations depending on what normalization is used, layer norms, batch norms, instance norms, all of them can have this, right? So it's a very simple time conditioning layers, and there is quite some engineering that one can do. These days people are using Fourier embeddings. So instead of just looking at time itself, they take some sine and cosine of time and embed it, thinking that it will provide them better frequency control on what's going on. But this is a detail, right? This may or may not give you any advantage. But the idea is to ensure that every part of your machine learning pipeline sees the input time. That is sort of the key point here. Clear? So everyone understands how this is to be done, and I think Bogdan has explained this at some point in the tutorial, right? This was done a little bit ahead, and I'm only coming to it now. Yes, go ahead.
What's the difference to passing it via residual connections?
You could also do residual connections, but even those have to be normalized, right? So everything has to be normalized. So it's sort of, so that's the logical way where you put this, because you don't want the convolutions to be affected or attention to be affected by this. So it makes sense to put it through this. Okay, so then let's, so you have this, so your operator, so there are two strategies. You can do autoregressive or you can do time conditioning. Autoregressive, there is, it's sort of plain vanilla, there's not much to do, right? You have been given solution, you just want to make next time predictions and you keep on doing that. With time conditioning, you have a richer sort of space to play with, and this is what I would like to explain a little bit. What is the richer space to play with? So now training strategies, right? So there are different kinds of training strategies. So remember that the simplest, okay, let me try to explain this so that everything is clear. So this is my data set, right? So I have the entire trajectory, and of course this changes with samples. This is just one sample. And remember, I did not even put in the velocity field, the coefficient, right? This is just the displacement, which measures the wave behavior. So this is one sample, and you have many samples, thousands of these kind of samples, right? Or input-output target pairs. So now what does one at a time training mean? One at a time training is simply that what you do is, given the initial conditions, this is not a good picture. So given the initial, so what do you do in training? So you have U0, U1, U0, U2, U0, U3, and so on, right? So just take the input-output target pairs. As you see, it starts with U0 or U bar. Again, sorry for the notational confusion here. Okay, I can use this as 0, right? And then U0, UK. So these are your data pairs. So all that you do is that here you take these two guys and tell the neural operator that match, given t equal to 1 and given this initial condition, match or try to fit this guy, the target here. Okay, so that would be your t equal to 1. Why is it not writing? Here similarly you do the same, t equal to 2. You say that given the initial conditions and time t equal to 2, I get a certain output. Similarly with t equal to 3, t equal to 4, and so on. That's why I call it as one at a time. And these are the data pairs. And if you have k samples per trajectory or k time snapshots per trajectory, then you get k training pairs, right? So a neural operator is given k training pairs, and if you have n samples or n trajectories, let's say 1000, you have 1000 times k. So this could be 20, so you have 20,000 data pairs, and you can train your neural operator to work with these 20,000 pairs, right? So remember that this is different from an autoregressive setting, because in an autoregressive setting, to go up to t equal to 5, I would repeatedly apply the operator. And this is not so easy to train sometimes. So usually in autoregressive settings, people only train for the next time step, or maybe they train 2, a rollout strength of 2. But here you can take any of it, right? You just say that at t equal to 5, given my initial conditions, this is the solution. Match it, right? So this is all that is happening here. Is that clear? So the number of data pairs now is k times n, where n is the number of samples. So if you have 1000 samples, this is 20,000. Which is quite a lot, right? So in particular for the weather, this could be a very rich set. But now this is not the only thing. The real thing here, and you could have guessed what is going on, is who stops me from saying that I just start at the initial conditions and predict solutions at a later time, any later time, but at a later time. I can start at any time and predict solution at any forward time, right? Because this is what a time dependent operator can do. My solution operator takes inputs at any time point and predicts solutions at a later time point. Why not use that for training? And this is what is called an all-to-all training. This is a simple idea, but to the best of my knowledge, it was introduced by us a couple of years ago. And what do you do in that? So we essentially just do that, right? So now my inputs are any of the possible combinations that you have. The only assumption that I'm making is that it should be causal. So I cannot say that given a t equal to 10, predict the solution at t equal to 8. That would not be the forward solution operator. That will be the backward solution operator. So in this case, okay, there is some, it really leverages this semi-group property, right, of the solution operator. So now what you do, you can have u0, u1, u0 up to uk. All of these pairs, they are very much allowed, right, from the initial condition. You can measure anything, but you can also start at u1. And from u1 you can't go to u0, but you can go to u2. From u1 you can go to u3, you can go all the way up to uk. So all these pairs, you can see the writings there. Similarly from u2, you can't go to u0, u1, but you can go to u3, you can go to u4, and so on and so forth. Now you can see how much of data we have at our disposal. So what does the neural operator or the operator, the solution the neural network, what is it trained for? Given the solution at any time instant, given a lead time, it matches the solution at the future time, and it takes all possible combinations into account. In practice, this is a very, very large set. So what happens now is that instead of having just k samples per trajectory, you essentially have k square samples per trajectory, right? So earlier, let's remember this, that we had 20 samples per trajectory, we had 1,000 trajectories, right? So we had 20,000 data pairs. Now we have 20 samples, but instead of 20, we have actually 210, because it's 20 times 21 by 2, right? So it's so you have 210. So now instead of 20,000, you have 210,000 samples. So you have much richer database than you had before. And the task of the neural operator gets harder. So it is it's forced to generalize better, because now it has to learn how to match things from from any unseen, from any point to any unseen time point, right? So this is sort of the main point here. So training can be done like this with different lead times. Inference you can do directly or autoregressively. What does it mean at inference? Maybe I explain it. At inference, suppose you want to learn the solution at t equal to 4, right? So by this method, given any initial condition, given the initial condition, and given t equal to 4, I can predict the solution, because my solution reads out any time and any point, right? That is one possibility. But I can also do autoregressively, because I know that I can go from t equal to 0 to t equal to 1, apply it again to t equal to 2, apply it again to 3, apply it again to 4. But that's not the only possibility. I can also go from 0 to 2, right? Because this is allowed. I can learn from any time and then autoregressively compose it from 2 to 4. Or I can go from 0 to 3 and go from 3 to 4. I can go from 0 to 1, 1 to 4. There are so many possibilities that you can think of, right? This is why it says it's multiple possibilities. And in particular, you can evaluate at any time, including out of distribution times, including any unseen time horizons. So this is a very, very flexible strategy. Okay? Is this clear? Are there any questions? I mean, this is a subtle concept. So one has to sort of do some examples. Maybe in the projects we will have some examples where you can learn this better. Okay, so now maybe we show some results. So let me just summarize before I show any results. So what do? So for temporal problems, we have this trajectory based data. So we have more data to play with. We have a harder task, because now we have to not just find the solution for a given input, but for any time point. So we can either use autoregressive training and inference, or we can use this kind of all-to-all much richer training with time conditioning and inference, which is much richer. So both possibilities, or there are many more in between combinations, but both possibilities are also there. So now let me, before I show you the results, maybe it's time to take a very, very quick break. Today, maybe I just... Okay, so now these are the different strategies that we learned before the quick break, and let's see whether it works in practice or not. So we come back to our familiar example. So this is Navier-Stokes equations, right? So Navier-Stokes. And the advantage here is that the boundary conditions are periodic, so you don't have to specify the boundary conditions, which makes life very, very simple. So then what do? The task is given u naught, the initial conditions, or u bar, whatever I called it. You find solution at any time t from whatever 0 to capital T. Yes?
Can we put the slides full screen?
Oh yeah. It isn't full screen?
Yeah.
That was strange. Okay, never mind. Okay, so the task is, and you remember this data set, right? So what I had shown you before was simply the solution at the final time. Now we have to look at the solution as an entire trajectory. So let us collect all the results that we have here. So what is this? It requires a little bit of work. So let's look at this one. So this is the same thing but in log scale. So this is in the linear scale and this is in log scale. So what you have here is the test error. So the test error tells you how much of error you make, and you're going all the way from 0.5% to 10% roughly, right? And this is the number of trajectories. Now remember, the trajectories is not just the number of time snapshots, but the number of trajectories that you have in the system, right? So we go all the way from, how much is this? 8 is 256 trajectories to about 8,192 trajectories, right? But for each trajectories we have this multiple time snapshots. I think 14 snapshots if I'm not mistaken. And these are, what you see here are how the error behaves at different times. Okay, so as you can imagine, as time goes on, the error keeps on increasing. Whatever be the strategy that you're adopting, the error keeps on increasing. Let's say 1024 trajectories with t equal to 0.2. So the beginning of the evolution, this is about 1%, right? At t equal to, what is it, 0.4, the orange one, this is about 2%, then it goes to around 3%, around 4%, and at the end it's about 5 to 6%, right? So the error is always increasing as you have more time. This is not unexpected. This is the same with numerical methods. It is harder to capture these, particularly if you have autoregressive, but in even the direct evaluation. But this error increase is only linear in this case. It's not exponential. This is what you want to avoid, right? If it's exponential, you are finished. So linear error increase is sort of very, very standard. This is what one would expect, and there is a secular belief in that. There's the first observation that you have. The second observation that you have is that at any time, as long as the number of trajectories increases, you have very nice scaling of error. So this always decrease, right? Let's take an example. So this is at approximately 2%, and then when you go to, let's say, 4 times that number, it's approximately 1%, so 0.5. This is exactly the same sort of scaling that you get. The scaling is approximately 0.5. It's a little less than 0.5. So this is very satisfactory. Error grows in time. Error decreases with the number of trajectories, the number of training data that you have. Okay. The second one, and this is very, very interesting, is okay. So let's try to focus again. There is quite a rich set of results here. So now what you do is, when we train this operator, this was based on CNO, but this is the same kind of results for every single neural operator that we have tested on, right? So what you do is that your trajectories, your data is sampled, your training data. So this is this input, right? So your training data is at t equal to 0, which we don't write here, 0.2, 0.4, 0.6, 0.8, and 1.0. Okay, so this is where your training data is. Now the test data is not just at these points, but at any arbitrary point. In principle, at any arbitrary point. Just for simplicity, we showed it at the other points, the uniform points, 0.3, 0.5, 7, 9, and so on, and 0.1. In the beginning, there is a large change. This can be fixed, and this was some preliminary results or old results. This can be fixed. by different, let's say, sophisticated state-of-the-art techniques. But in the beginning, you are directly going from t equal to 0, where nothing happens, to something dramatically changing or something changing, large gradients. So the errors are large, so you can just dispense off. But then you can start seeing that essentially from here onwards, the errors are almost, it's as if it is nicely interpolating between these time points. So you can evaluate it at any time point, and the error behaves exactly as it would behave as if you are interpolating, right? So in a way you can think of it as a smart interpolation, but it is beyond that, because it has never seen this in the training data at all, right? So it has to get this information from the dynamics itself, and which is not always obvious. It's not guaranteed that this happens. So this is precisely this continuous in time property that has come. We can improve it much further, means later on we have improved it, but already at this level you can see a manifestation of this particular property that that you have this sort of behavior here. So you can see that the error is quite well behaved. So it can be evaluated at any point, which is the key question or the key issue here. That's why we say it's OOD time levels, right? Then this is an interesting one. This is different inference strategies. So remember that t equal to 1. So to go to t equal to 1, so you start with you have t equal to 0, 0.1, 0.2 rather, 0.2, 4, 6, 8, 1, something like this, right? So what we do is that you have a direct. So what does direct mean? Direct means that to find the solution at t equal to 1, you at inference, you give it the initial conditions and you give it time t equal to 1 and read off. So as you can see, as the number of trajectories increases, the error secularly decreases, and with direct you have, so these are some of the rates that are there. With direct, this is the error that you get, right? So you get about 4% error with 2048 trajectories. But remember, I told you that why should we just use direct? That's the simplest, the fastest in a way, because it's just one shot, right? You just give it one time and then it finds the solution. Here we have given different kinds of things. So autoregressive would be, because we have 10 snapshots here. So you start with 0, go to 0.1, 0.2, 0.3 and so on. So the autoregressive in this case is actually better, right? Just at inference. But remember that I also have to infer it 10 times now. So the inference itself is 1 millisecond. So 10 milliseconds doesn't really matter in this application, right? But autoregressive, as you can see, it does clearly does better. It's halving the error. Why it happens, who knows? Means it's sort of, it's in this, not even a half. Is it a half, or it's, yeah, it's like 2% and 4%. So in this case it's easier, because to learn from 0 to 10 is not easy, whereas to learn from 0 to 1, 1 to 2, 2 to 3 is easy, and the error accumulation that you get in this case is less than the error that you're making when you're doing a direct march, right? So this is one thing which is difficult to get a theoretical guarantee on, but this is an observation. But now in this case, the strategy that works the best are the red and the green lines. So for instance, let's look at the green line. This is the one that gives you the best error. It even halves the error significantly. So what you do in the green line is you go from 0 to 1. Okay, we know that that's a hard thing to do, because in the beginning a lot of things happen. So you go from 0 to 1, and then from 1 to 4. So you go directly from 1 to 4, 4 to 7, 7 to 10, right? Means this is the strategy, and this gives you a much better error across all the levels. This is based a little bit on expert knowledge. You know that in the beginning there's the initial layer and then there is a smooth evolution, so you do that. But actually even what didn't work is the 5-5. Well, it did work, but the other one is also working, which is go from t equal to 5, then 2 and 3. That also works. So there are different strategies that you can try. So this is left to the end user's choice, right? Once the training has been done, it is at your choice to see how you do inference, right? You can do inference in an autoregressive manner, you can do inference in a direct mode, or you can do inference somewhere in between. Yes?
To clarify, is this all from network trained on the all-to-all?
Oh, this is with all-to-all. Okay. This is with all-to-all.
Okay, so yeah, you said like it's started just related.
Yes, everything here that I'm saying is about all-to-all. Okay. But in the next one, I think I compare the two. But so far it's all-to-all, because it gives you the freedom, right? It sort of tells you that you can use this autoregressive strategies in an effective manner. Further questions? No? Now here is the comparison between the different training strategies. Okay, so so vanilla is one at a time, right? So this was not vanilla; it's one at a time. And all to all is the strategy that I showed you, and it gives you a lot of it gives you some advantage, but it's not a massive advantage. It gives you some advantage. Let me show you what. So let's fix the number of trajectories. The number of trajectories is still the same. So the data generation costs are still the same, means it's exactly the same amount of data. Let's look at this. So you have 1024 trajectories, and you are looking at the solution at t equal to 1, probably in the direct mode. Now I don't remember the exact strategy here. So this is 0.5% error or 5% error, 5% error, right? And then if you do the all-to-all training, this is with the all-to-all training. With the plain vanilla training, you have about 7%, 8% error, right? So the error does go down because you have more data now. The error does go down, but it doesn't go down by a huge factor. It does go down because you have more data intensity, and this is secular in the sense that each time we have observed that you have a steady decrease in error. But the main advantage of this is, of course, that you can reduce the number of trajectories, because the data generation costs, I can tell you that at large scale, maybe at the very last lecture, I'll show you some mind-boggling numbers which are almost at the ChatGPT scale. The amount of the compute cost for data generation is like 1,000 times or 10,000 times more than training the model. So it's sort of there is massive data generation costs. So if you can save on data generation, then it's always a boon, and this is what really happens. So if you, for instance, instead of 1024 trajectories here, if you draw a line, we are somewhere around 512 trajectories, right? So use half the data generation cost. Doesn't look like a lot, but at scale, this is like $1 billion. So this is a real, it might not matter a lot, but it does matter then. Question?
Yes, in practical applications, is there any argument for not using all-to-all?
Storage.
Okay.
It's not even that. The model training. So I'm sorry, it's not storage per se, because you'd anyway have to store also for the other kind of training, right? But I would say model training costs,
Okay, right.
because it's more expensive to train, and
K-squared.
it's k squared, but in practice that's a huge number.
Yeah.
So if you have 10,000 trajectories, this is a huge number, right? So you 100 time steps, it's still a big number. So what you do is that instead of doing it k squared, you take a certain proportion of k squared, which you decide randomly, right? Because then you can randomly per epoch you can change, and then the training cost. But there is absolutely no reason to not do it. Because the training costs are vastly dwarfed by data generation costs. But if your training costs means not everyone has access to huge supercomputers to train. So if you're sitting with your little laptop and you want to do training, then you will probably do what is the most effective one, which is not necessarily all to all, but some version of it where you randomly sample, because it makes sense for a neural operator to make its training task as hard as possible so that it generalizes well, right? So this is sort of the principle. But anyway, coming to your point, this is a very interesting result. It has a lot of content in it, so it's important to, because now all to all, as you said, the question was with all to all, it's there are so many things that you can do, right? So for instance, here what we show, there are a lot of things. Forget about this autoregressive and direct, right? Because this is just the two modes of inference. This is, but what is this T2 and T1? So T1 is you do all to all, but at a resolution of all the 20 time snapshots or 14 time snapshots that you have. So you take each of these 14 time snapshots and you train 91 pairs. Whereas T2 is with 7 of them. Okay, so with 7 of them, which means that you not randomly, but you uniformly choose half of them, and then you just use all-to-all training on that. So you reduce the number from 91 now to how much is 7 times 6 by 2, so 21 or something, right? So you reduce the number by half. And then you see that there is some saturation, means these time trajectories are not totally independent of each other. Only in a completely chaotic system with no memory will this be completely independent of each other. But essentially the information that is contained, particularly with very small time increments, is not a lot of information. Okay, so what the model trainer has to decide is what is my effective resolution where I can learn something useful and not burn my training compute, right? So these are sort of dynamic decisions that one has to make, and in this case it is that instead of taking all the all-to-all pairs, if you take half of them, it's good enough. Sometimes maybe 1/4 of them is good enough. So this is sort of a dynamic thing, and so that's the first thing, that there is a saturation. Just because you keep on taking more data doesn't mean that this data is that this is going to lead to a decrease in performance or something. Can anyone give me a mathematical or a semi-mathematical reason why this is the case? Because what have we learned? We have learned that more data when we randomly sample from a distribution leads to better performance. But in this case, at some level it gets saturated. Who can tell me why? Yeah?
Well, from information theory, as we draw samples from a distribution, it adds marginal information.
That is true, but here these samples are no longer IID. That's the main reason. These are not independent samples because they are highly correlated to each other. So if you take the information content that is there in 100 of them is not double the square root of 2 times the information content in 50 of them. It's much less because these are not IID. So that's the main sort of reason. But nevertheless, there is some information content, right? It's not the content between 100 and 10 is not 0. There is some gain in information, but it's not a dramatic gain in information. And the last point that I want to make, and then we can stop about time dependent operators, is a very interesting one. So this is that, so we do the same thing here. So T14, so this one is essentially, so this is the direct mode essentially. So what you do is you just take, this is what we were doing before. Given the initial conditions, just find the solution at a final time, right? So with that, as you can see, for instance, here the error was, I don't know, 20% with 512 samples, okay, in this particular example. Now with the same data generation pipeline, of course with a different model training pipeline, what we have learned with this all-to-all, with autoregressive inference and so on, how much do we reduce the error, right? So as you can see, now with 512 here, you go somewhere down here, right? So this is exactly the same quantity that you are comparing, but now it's the cumulative strategies that we have accumulated. So all-to-all training, autoregressive inference, and when we combine them, we see that instead of 20%, we are at now 10, 9, 7, 6, 5 or something, 5%. So we reduced it by a factor of 4. Right, so this is a massive gain in with the same, the data generation pipeline is exactly the same, but now by accumulating this, I reduced the error considerably, and not only that, I also reduced the number of trajectories that I need, right? So for instance, this was with 128 trajectories, and it is very, very similar error to the 512 trajectories. So essentially, I can reduce the data generation cost by a factor of 4 or 5. So there is a benefit of doing all this, but it's not like a 512 times benefit, right? It's a moderate benefit. But as I told you at the top end, this 5 to 10 is a huge number. So it's very, very important to have these innovative strategies in place. So I think that's all I wanted to say about time dependent problems. I think you have had a tutorial on this at some point, right? It was not the one, but the one before, I think, CNO time dependent. So you can sort of reconnect with that. And when you deploy this in practice, when you go in a lab or when you go and in a job, you remember that, hey, there are different possibilities for using time-dependent training and inference. Okay? Any questions? Yes, go ahead.
Active learning in some way used because
Active learning, yes, but not in this context. Here, the interesting thing that is coming on is what is called online learning. So online learning, the difficulty with time-dependent data sets is you have to store data, right? And you imagine that in your experiment, if you're generating per time step terabytes of data, then you have to store, and there is storage is limited. So what people are doing now is that they are experimenting with how to sort of keep on learning the models simultaneously with generating the data. And once this is, there are some preliminary attempts, even we are involved in some projects in this. But once this is sort of established, then this can be done at scale and can be combined with active learning. Because what active learning does, maybe at the end of the course I have time to come to active learning, is to sort of sample data in such a manner that you have an objective which is achieved, which is to reduce the error, for instance, right? But if you have to store all the data and then decide, then this becomes unaffordable. So here in this context, online learning is more important than active learning. Or active learning is anyway, with any operator learning, this is an important point. Okay, so now we go to the next caveat, which I'll just start. I'm not really going to do a lot of work on it, but let's just start. So the first caveat was time dependent problems, and as I said, for time dependent problems there are lots of solutions which are available, and you can really augment or improve your methods by doing many of these tricks. But the second caveat, and I'll spend quite a bit of time on this, is what happens to PDEs but on arbitrary domains. So far what we have shown is something very sort of Cartesian, right? I had examples, everything was on a unit squared, and I showed you, at least it was on a unit squared and not on the unit interval, but it's still on a unit squared, right? So in principle we were just doing problems like this so far. But engineering, and especially engineering, sometimes physics, but especially engineering is not like that, right? So look at this, I don't know how well you see it. Now you can see it well. So this is a flow past an airfoil, right? So this is 2D, 3D, it's even more complicated, difficult to visualize. You see it in the next example. So this is an airfoil, and this is where the data for the airfoil comes from, right? So it comes from a numerical simulation, and the numerical simulation understands, or the person making the numerical simulation understands, that A, you cannot represent it on a Cartesian grid because there are geometries here, right? B, that this grid has to be highly adapted because there are some shock waves, there are some different features. So this is an actual example of a mesh that was generated by one of my students in our lab, and you can see how dense or how different the data format is. So remember, here everything was uniform, it was points on a square. Now here the flow field is given at these points, at these tiny little points, and you can imagine there are lots and lots of points in this region because a shock is going to form in this region. So there is no uniformity whatsoever, it tossed out immediately. So whenever you do an engineering application, you cannot work with Cartesian grids. That is okay for learning about something. It's okay to some extent to learn about physics, but engineering is about real world when the shapes are going to be very complicated. So whatever we have done so far does not necessarily apply in this setting. And here is a real industrial scale example. This is a actual model of a race car, right? And you can see that this is just on the surface, because if I showed you the volume, then this would be complicated. But this can be aerodynamic forces when the car is moving, because it's the air exerts a force on it, or it could be loadings, right? It could be that someone is trying to put a hammer into a car and try to break it. Means both of them some sort of loadings. And now you can see how complicated the mesh is. I mean, this is for aerodynamic purposes, right? So you have lots of points here on the tires, in the tail fin, right? This is a very complex distribution of points. So input and output are going to be on essentially point clouds, very unstructured meshes. So this is sort of the main point here. So far our focus has been on something completely different. It has been on Cartesian domains, so this uniform grids, but most real world PDEs are on arbitrary domains, right? Like the examples that I just showed you, and they're discretized with very unstructured grids. And ideally, if you could just treat point clouds, that's the best. Means you should not even have a notion of a grid, because to store these things is quite expensive. So to convert what we showed, some preliminary positive results on Cartesian grids, perhaps time dependent or time independent, it doesn't make a difference, to this is a massive challenge, right? And this is what is required in order to scale AI to real world physics and engineering applications, and we need to be able to handle such data. So a little bit in today's lecture, but essentially in the next lecture I'm really going to cover this topic at some length, right? So is the challenge clear? So you cannot use now convolutions, we cannot use Fourier transforms, all of this gone, right? Because it's they're all based on a Cartesian. Transformers can be used still, right? Because it's essentially operations with respect to points, but some of the tricks there are also gone. So as I said, what is the available methods? There are many, but we will explain a few of them. So one thing that we can do is to sort of convert it into a Cartesian domain through what is called masking. So what does masking imply? Masking is, let me explain it a little bit here so that you get the context. So it's true that my data, which is given from the numerical solver or from measurements, whatever, is given on a very complex point cloud like this. But once the data is there, I can always sort of interpolate it into a Cartesian grid. So what I can do is, okay, I say fine, I have this data which is on a very rich domain, but let me just take a very simple Cartesian grid. Just for illustrative purposes, I am using 16 points, right? You cannot use 16 points in practice, but you can do whatever, 64 by 64, a Cartesian grid, and I can superimpose a Cartesian grid on this particular picture, right? But what will happen to my domain here means there is no flow inside this, the flow only happens on the outside. You mask it. You simply say that there is a mask, a binary mask, which says that there is 1 on this domain, nothing happens on inside the airfoil, and it's 0 outside the airfoil. Things happen outside the airfoil, or the other way around. So this is masking. You can convert many things into a Cartesian. Once it has been done, you can convert it into a Cartesian domain, and perhaps later on we'll show you some examples of this. But you can easily see that this is very unnice, right? Because the operator is not well defined, the resolution of the geometry is not there. If you do it something with a race car, then you will not be able to do this binary mask very nicely. So this is a cheat, right? Can be done maybe as a baseline, but it never provides satisfactory answers, never understands the geometry, right? So this is one of the issues. Of course, FNO, for instance, means it's based on a Fourier transform. So if you remember FNO was right. So you have the Fourier transform, which is an integral, right? It's whatever f of x e to the 2 pi I kx, something like that, dx, right? And so in principle, this is a well-defined object, means a Fourier transform is defined on any domain, means nothing prevents us. The reason why FNO was restricted to Cartesian domains was because of the fast evaluation through FFT. FFT only works on Cartesian domains. You know, that's so if I want to directly evaluate this integral, a Fourier transform, then this is order of m squared. M is the number of points. With FFT, you have m log m, right? So this was the reason why computational complexity was reduced. But you know, in this paper which came out a couple of years last year, I think, from the lab, what we showed is that you can replace this with just a numerical quadrature. But the only reason why this quadrature works is because you don't need too many Fourier modes. So if you remember, in FNO, we never needed more than 24 or 20 modes or something like that, right? So we took a very complex data set and we reduced it into 20 or 24 Fourier modes, and then you operated on that. So this can be done by using what are called direct spectral evaluations. This is often a baseline that we used, but again, there is no geometric understanding. It's still a Cartesian domain method that we are cheating by simply evaluating the Fourier transform in that manner. So it's still a viable option. But the option that is very popular, particularly in industry, is what are called graph neural networks. Okay, my hope was to start with graph neural networks today, but clearly I've run out of time. So in the next lecture, we will give you a very sort of a short introduction to graph neural networks. I won't really have time to explain this in graphic detail, pun intended. Because first of all, there will be a full tutorial on graph neural networks. Second, David, who is going to teach AI for chemistry and biology, he will also explain graph neural networks. So I will go through it very quickly, explain its advantages and also its disadvantages. And then in the next lecture, already switch gears and go for a combination of graphs and transformers that I believe is the right approach for these problems. Okay, so next lecture, in the beginning, the first half is on graph neural networks. The second half is on a combination of graphs and transformers that sort of solve some of the problems of graph neural networks.